Okay, time to beginning here. It was a very rough night. I don't know about you guys, but I was actually very shocked and startled at the outcome of the election. It was not what I expected. But for those here in Nebraska, the death penalty is back in play. Ernie Chambers promises to have a bill in January to once again repeal it. And
so much back and forth on that.
The bond for property tax lost a 2-to-1 rate. So those are things that I considered important. Actually, the people in Southwest are real excited about that. I don't see Jasmine, Carrie, Brandy, or Jordan. Is that okay? Carrie and Jordan, I know, are doing the acrobatic thing. All right, let's get going. I have a very optimistic schedule. So getting started. Methods of heating. We have the first method here, conduction. Conduction is a method that has direct contact between two things. I'm going to go to the next slide and come back. The actual mechanism for conduction is very simple. You have two materials, particle in one material that's at the edge, hits a particle in the edge of the other material. You have a collision between the two, and you transfer energy. And heat is that transfer of energy without having work done. If there was work, I would have had force and a distance. So I actually would have had to have, my sample moves because of it. Microscopically, there was the motion, but macroscopically, there wasn't, so we call it heat. So this picture just shows an example of a faster moving particle hits a slower moving particle, and after the collision, you have some transfer of energy, and so the faster one slowed down, the slower one sped up, and as a result, the energy that was in the higher temperature one transferred over to the lower temperature. And as I said numerous times by this point, one statement of the second law of thermodynamics is that heat naturally flows from the hotter temperature to the lower temperature. You can have a collision that makes heat flow the other direction, but if you take the macroscopic behavior, that is looking at all of the molecules and taking the average of their transfer, it's always going to have the averages going from the higher energy to the lower energy. That is the higher temperature to the lower temperature. So when we talk about conduction, the conduction has to have something to do with how much area of contact you have, because if there's no area of contact, you're never going to have the molecules hit each other to have that transfer. And so the power, that is the rate for heat transfer, has to be proportional to the area. Assuming that you have a hot, looking at this picture, it displays the assumption. You have a hot region and you have a cool region, and you have some separation between them. It's going to take time for heat to flow from point A to point B. And the longer it has to travel, of course, the more time it's going to take. So the rate is inversely proportional to the length. Finally, the bigger the temperature difference, the more energy you're going to have transferred per collision. And it turns out it's linear. So the conduction rate is proportional also to the temperature difference between the two sides. In every one of these, I said proportional. So that leaves one thing left in my equation, K. K is just called the conductivity. And you'll notice here it said thermal conductivity because we also could have talked about electrical conductivity. And so that is the constant of proportionality to go with all of those, proportional to area, inversely proportional to length, and proportional to temperature difference. And it depends on what the material is, what that conductivity is going to be. So here's a list of those thermal conductivities, the K values, for different materials. So this list tells you what's a good conductor, what's a poor conductor. If you look at this, you'll notice something pretty clear. These things up here are metals. Metals have high Ks, that thermal conductivity. A high K means that the rate that heat flows through is high. So they're good conductors. Metals are good conductors. They're actually both good conductors of electricity and good conductors of heat, and for the same reasons. So metals are good conductors, and you can see here silver's a really good conductor of heat. Copper is much more common, and it's a very good conductor of heat. When I was in graduate school, I was doing some experiments where I had to do soldering on a brass piece. And if you've ever tried to solder on brass, it's really hard because you put that really hot tip of your soldering iron on the brass, and the heat quickly flows throughout the entire brass, which means that you have to heat the entire thing up before you can get hot enough to start melting solder. And so instead of using a solder gun, we put it on a hot plate like the one I brought out for lab, and we just heated the entire thing up, and then you just put your solder on and melt it, because soldering gun's just never going to get it hot enough. It's not putting out enough power. So gold, you see, is a good conductor. Aluminum, not as good. And then you get down to iron and steel, and it's actually surprising how bad steel is compared to these other metals. But those are good conductors, the metals. Then we have the things down below that we tend to call insulators. The insulators, and one of the common things you see in insulators is they're less dense. Less dense, well, that means that your atoms aren't going to have as much contact, right? And in fact, you'll notice air is very low on the conductivity. Air is a really good insulator. And so we take advantage of that. If I look around the classroom, I see people wearing things like a sweatshirt. Well, what does the sweatshirt do? It traps air. And so that air being trapped means that you don't have good conduction of heat going away from your body. And so you trap that heat in, and it keeps you warm. So that's the point of air. So you go snow skiing, you wear your, thermal underwear, whatever, long johns. You're just wearing something to trap air, and you're using the insulation of air. So if you look at these things down at the bottom of the list, styrofoam, that's polystyrene that has a bunch of air blown in it, and the air is all trapped, and that's what's giving you your insulation product, or your insulation, let's just say that. Down feathers, you're trapping air bubbles in the feathers. Wool, you're trapping air bubbles in the wool. Glass wool, well, unsurprisingly. Snow, all of these, you're trapping air. It's the air that's really the good insulator there. Looking at this helps you understand how you can make an igloo and sleep comfortably in there. Probably don't do this at Southwestern, but here at Union College, people in IRR, pretty much every year, they'll go build an igloo out in front of the Dick building and sleep in it or something. Igloos, you think that's ice, it's going to be cold. But you see that ice is a reasonably good insulator. If you don't pack it as much and you have it more like snow, that is, if you have more air, it's a much better insulator. And so you make that igloo, the walls are cold. The walls are cold because it's ice. But the rate that heat flows through them is going to be relatively slow. So if you can have the air temperature inside reasonably high, 70-ish, 60-ish, it's going to take a long time for that heat to flow out, and so you can keep it warm in there. Of course, you will eventually melt the ice if it's not cold enough outside. So that's how an igloo works. First clicker question here. Which material is the best insulator? Remember, best insulator would mean the worst conductor of heat. Okay, cut it off in about 5 seconds. Okay, stopping it here. We have 6, 3, 21, and 16. So there was no majority. We just had election. We all probably paid attention to the difference in a majority and plurality. We had a plurality for error, but not a majority. Cody Johnson, give us your answer and your reasoning behind that answer. Okay, Cody's answer was he chose C because just 30 seconds ago I was talking about what a great insulator it is. What about wood? Where would wood fit in our insulations? Would it be good, bad? Okay, relative insulator. It's a relatively good insulator. These ones at the top, those would be good conductors. Which one would be the best conductor on this list?
Copper.
Copper, the best conductor. So in order of conductivity, the best conductor is copper, then iron, then wood, then air. And we could come back and check this here. We have copper, iron, wood, and air. So wood, that's a pretty good insulator. You build your house out of wood. It depends on the kind of wood, how good the insulation is. But that's a pretty good insulator. Now, back in the day, like my grandmother's house, truth. You guys know that they had those internment camps during World War II, right? And so after the war ended, California allowed people to come and take the building materials from those internment camps. So my dad's family, being dirt poor, they went and they just harvested materials and built their house out of stuff from internment camps. And they wanted insulation because it gets a little chilly in Chowchilla, California. So they put newspaper in there. Newspaper, well, that paper is largely wood, but it wasn't the wood that was the purpose. What was the purpose of the newspaper? To trap air, so that the air was the insulation. And of course, that's kind of dangerous because that wood is flammable, and then they just have, bare wires running through there for electricity, and the wire gets hot, and the wood, not perfectly safe. My other grandmother's house actually caught fire because of those bare wires getting hot. So not perfectly safe. The next one of our, great. You can see that there's something on here. There we go. The next one of our heating mechanisms is convection. We do not have an equation for the rate of convection, the power for convection. But convection is when you have an intermediary. So you take something like, we have an oven that's a convection oven. You have a hot element, then you have a fan that blows air over the hot element, so you have conduction from the hot element to the air, and then the fan blows that over to your food. And then the hot air will have conduction from the air into the food. And so the convection was the heat was transported by an intermediary, in that case the air. So that's what convection is. An intermediary is transporting the heat. And convection is really important for things like weather. Because on Earth, we have the equator tends to be warmer. And because it's warmer, the air at the equator gets hot, right? Heat goes into it. And what happens to hot air in terms of the volume? If the pressure stays the same, what happens to the volume? It expands. And if the volume expands, that means the density dropped. And so that hot air floats up. So here would be the same as having the equator where you're heating air and the hot air floats up. Well, as it floats up, the pressure becomes less, it expands, and using your ideal gas law, if you expand, that is going to make the temperature change. What does the temperature do if you expand? PV equals nRT. Okay. As it goes up and expands, the temperature is actually going to drop. And so it cools as it rises. But as it cools, the moisture, you can't hold as much moisture. You might remember the graph from last class period where I talked about the dew points of air. It can't hold as much moisture. The water or the air there at the equator tends to have a lot of moisture in it, but it goes up, it cools, and the moisture drops out. So if you live near the equator, you're going to get lots of water, lots of rain, because of that hot, moist air going up, expanding, going up, cooling, dropping its moisture out. Then it gets up to higher atmosphere, and it's got to either go north or south. It's going to go toward colder regions. And so the air goes in the upper atmosphere, and because it's now cold air, it will start falling and be compressed as it falls. Now, this is where the picture here is not indicating what's going on weather. As the air compresses, what's going to happen to its temperature? It's going to go back up. So now you're going to have hot air coming down. But it's dry because it dropped its moisture as it went up. And so it comes down, and you have hot, dry air that comes down and hits the earth. And if you have hot, dry air, what do you call that environment? Yeah, a desert. And so we have deserts where we have the hot, dry air coming down to the earth. They tend to be about 30 degrees north or south of the equator because of that hot, dry air coming down. And so we have these convection cycles that are going on all the time. The air up here in the top, because of the Coriolis effect, that's what creates our jet stream, so you can fly faster one direction than the other. And we have smaller effects living near the ocean. Well, let's talk about that in just a minute. Purpose of hair, trap air. Trap air so you don't lose or gain heat. My head is not doing as good a job as it used to. On the other hand, my back is doing a swell job. Moving on. The third mechanism for heating, the third and final, is radiation. Radiation is the transfer of energy through electromagnetic waves. And we'll study electromagnetic waves carefully next semester. But with this transfer process, we again have an equation, and it's a little surprising. The rate of heating depends on temperature raised to the fourth power. So it's very heavily dependent on temperature. If you have something that's twice as hot, 2 raised to the fourth power is 16, it's going to radiate 16 times as much energy per second. The other terms you have here, the Stefan Boltzmann constant, I believe is the name of it. And I point to the wrong one. I point to emissivity. That's the Stefan Boltzmann constant. It's just a constant, so you look it up in a table. That script E or epsilon, point to it there, is the emissivity, which is telling us how effective something emits radiation. It turns out that things that are black, we probably know this. If you go out on a hot day wearing a black shirt, what happens to you as far as getting hot or cold? You get really hot because black is really good at absorbing electromagnetic radiation. And if it's good at absorbing, it's also good at emitting. And so we call this process black body radiation because black is the ideal color for this process. If you have something that is silver, I'm a fan of the silver and black, the silver reflects everything, and so it doesn't absorb anything. And of course, white reflects a lot, so white is also a very bad black body object. So the Raiders, up until last week, Rachel, and up until last week, the Raiders had played a lot of games on the East Coast, and it's still sunny. And so all but one game until last week, last week was a home game, so they wore it again. They had worn their black uniforms because the home team gets to choose what color they're going to wear. And every team has a light color and a dark color. And so if it's hot weather, the home team is going to choose their light color so their players aren't absorbing as much radiation and not getting as hot. Gives them an advantage. If you want to talk cheaters, there is, once again, this team from Colorado where they don't have quite enough oxygen that went to play a game in sunny San Diego, and they didn't pack their dark jerseys. So they got there and said, oh, we only brought light jerseys. I guess you guys have to wear the dark jerseys and we'll have to wear the light ones. And the NFL just let them get away with it, which I found pretty astounding. But that's just because of basic physics. So let's say that you are in a sauna and you want to calculate the rate at which you are receiving heat into your body from the sauna. The way to calculate that net rate of heating is to take this equation and this lower equation showing the net rate, so it has two temperatures. You're going to have the constant, Stefan Boltzmann constant sigma, and then the emissivity, which is going to be how effective your body is at absorbing and emitting radiation. And for the human body, it's reasonably close to 1, actually. Then you have the area of your body. So you'd have to calculate how much surface area you have. And then you'd have the temperature of your body to the 4th power minus the temperature of the room to the 4th power. And so your body temperature, of course, is somewhere around, 310 kelvins. And if the room is at, let's say, 320 kelvins, you could put it in the 310 to the 4th power minus 320 to the 4th power. That difference is the number then that's going to tell you about how quickly you're heating or cooling. Now notice, what units did I use for temperature? Kelvins. You have to use kelvins here because it's temperatures, not change in temperature. If we go back to the conduction equation, all the way back here, that was change in temperature. For change in temperature, you can use Celsius or kelvins. Either one works because a change of 1 degree Celsius is the same as a change of 1 Kelvin. Okay, so this is just showing what's going on with radiation. So we have something that's black for the top 2 pictures. And if you have radiation that comes and strikes that black surface, most of the energy will be absorbed. A small amount will be reflected. And if you reverse it, you have a lot of, you have energy in the object. When the energy gets to the surface, most of it will come out and only a small amount stays inside. And the fraction between those is the same whether it's coming in or going out. Silvered object, it's going to be just the opposite. You're going to have most of the energy is reflected whether it's trying to come in or trying to go out. You put those together and you have the silver and black attack. Have you guys seen these thermographs? They're really cool. What you see here is looking at the infrared radiation. Infrared is telling you that it's wavelengths that are frequencies below the frequency of red light. When I was a young buck reading the encyclopedias, I interpreted this as infrared because I didn't know what I was talking about. It looks like infrared. I still stand by that. But infra means below. It's below red. And so that infrared radiation, you're giving off radiation right now. And if somebody uses a night vision scope, they can see you because they're seeing that infrared radiation you're giving off. And so this thermograph is taking that infrared radiation and calculating based on the peak frequency what the temperature is and giving you different colors for the temperatures. And so you can see, for instance, where more energy is escaping. And so where it's red, like here, places where it's red is where you have the most energy escaping, then yellow. You get down to the blue and there's very little energy escaping. So you can see these windows in the bottom are emitting a lot of energy, which stands to reason. You probably have your poorest insulation around the windows. Upstairs, they probably don't have the heat on upstairs because you don't have as much radiation escaping from upstairs. One last thing on these heating mechanisms, the greenhouse effect. Does the Earth have a greenhouse effect? Yes. Is that a good thing or a bad thing?
It's a good thing.
Okay, I have some different answers. I heard mostly good, I heard depends. I want to talk about this because, whether you're going to go into physics, medicine, or psychology, having some understanding about a topic that is globally relevant is beneficial to you. And the greenhouse effect is clearly something that is globally relevant. So what's going on with the greenhouse effect? The basis of the greenhouse effect is that the sun has its peak radiation. Come on, really? Sun peak radiation in the visible range, somewhere around 500 nanometers in wavelength. So the sun is giving off this radiation about 500 nanometers in wavelength. And if you look at the yellow here, the yellow is the energy coming in from the sun. So we have about 342 watts per meter squared. Watts per meter squared. A watt is a joule per second, power. Per meter squared is then saying power per unit area. We call that an intensity. So this is the intensity of the solar radiation, 342 watts per meter squared.
Why does it say meter to the negative 2?
Because m to the minus 2 is the same as 1 over m to the 2. So it's a way of writing per meter squared. If you look at that, just about 50% of that radiation makes it through the atmosphere to the Earth. About 50% of the sun's radiation makes it to the Earth. You have around, and I actually calculated these numbers before class, around 22.5%, so I'm going to say 23% of the solar radiation is reflected off of the clouds. Never comes into the Earth's atmosphere per se, just is reflected out. And you have about 20% that is absorbed into the clouds up in the atmosphere. And it's right around 50% that is absorbed into the Earth. And then this here is just, 30 would be about 10% that hits the Earth and is reflected. So that's the radiation coming in. Now with the radiation leaving the Earth, if you look at the red here, it's showing 390 same units of watts per meter squared leaving the Earth. Let's not worry about why the number is different. You have to have a balance. But of that 390, only 40 makes it through the atmosphere. So 40 out of 390, that's about 1/10. So about 10% of the radiation gets out of the atmosphere. The rest is absorbed by the atmosphere. And that's what the greenhouse effect is really about. 50% of solar radiation gets in, 10% of Earth radiation gets out. Why the difference? Because the solar radiation is visible with its wavelength around 500 nanometers. The Earth's radiation is infrared, NF, infrared. So you have the wavelength for the Earth is about, I gotta see if I can do this in my head. I'm pretty sure I'm going to be wrong, but I think it's somewhere in the ballpark of 10,000 nanometers. It's a much longer wavelength. It's 3 million divided by 300. 3 times 10 to the 8 divided by 3 times, or not 10 to the 8, 3 times 10 to the 6 divided by 3 times 10 to the 2. Yeah, I think that's right. So about 10,000 nanometers. The different wavelengths are what makes the difference. The atmosphere is pretty transparent to the visible light, but because of certain gases in the atmosphere, it absorbs these longer infrared wavelengths. So you have to have a balance. If we're going to be in equilibrium, the energy coming in has to be equal to the energy going out. If we have more energy coming in than going out, then the amount of energy we have is going up. And what does that mean for temperature? Temperature goes up. If you have more energy escaping than comes in, what happens to temperature? Goes down. And so what's going to happen is you're going to have the Earth try to find an equilibrium, so it's going to get hotter or colder in the clouds until you have the amount of radiation that leaves the clouds is equal to the amount that's coming in, so we have a net balance. So this effect, if there was no atmosphere up there at all, then we would have this 77% would not be blocked, the 67% would not be absorbed, and we would just have, the 10 and 50 numbers for what's absorbed and reflected. So you just scale those, 50 divided by 60 and 10 divided by 60 for the fractions. And then leaving, everything would get out. And so if everything gets out, what would happen to the temperature? We would drop. And so we would reach a balance that's colder. So if we had no greenhouse effect, we would be very cold. If you look at Mars, the next farther out planet, Mars has an atmosphere that's about 1/100th as thick as ours. And because it has that thin atmosphere, it has a very, very lame greenhouse effect. And because of that, at the hottest parts of Mars, it gets as warm as what it is outside right now. The coldest parts of Mars is bitterly, bitterly cold. Like we would be frozen popsicles and then some. It's colder than our deep freeze we used yesterday in lab. So without the greenhouse effect, parts of Mars are way too cold. Only when it's sunlight do you get warm enough for there to be life. And the Earth would have a similar thing. If we didn't have a greenhouse effect, we would have it get too cold at night for life. And so basically, without the greenhouse effect, no life. Well, we have another planet closer to the sun. Now, you might notice this and say the obvious. Well, the one closer to the sun is getting more solar radiation just because of proximity. The one farther from the sun is getting less solar radiation because of proximity. Those are true statements. But this other statement about the greenhouse effect is also very significant. Venus has an extremely thick atmosphere. And because of that extremely thick atmosphere, it has a really, really large greenhouse effect. And that greenhouse effect makes it so the temperature on Venus, year-round, day or night, is in the ballpark of 800 degrees. We can't live in that, right? The Russians are the only people who've actually sent spacecraft to land on the surface. And their longest surviving spacecraft survived for just under 2 hours for two reasons. Number one, it's a pretty hostile environment. It's very acidic, and so it etches the metals. And it's so hot that it softens and melts metals. So they have what we call a runaway greenhouse effect there on Venus because it has too much atmosphere. Mars, no greenhouse effect to speak of because it has too thin. The Earth, we're just right. I believe that's because God created the Earth and gave it the conditions for life. So how does man play into this? And I'm going to ask a question that most people don't know the answer to. What is the most important greenhouse gas? I heard somebody say water. That's the correct answer. Water is the most important greenhouse gas. Al Gore never talks about the water in the atmosphere. Why doesn't Al Gore talk about the water in the atmosphere? No, we're not here to malign people. What effect do you have personally on how much water is in the atmosphere? None. You can't control that. When Al Gore is talking about, and I talk about Al Gore because he's the one that made it in everybody's mind, he was talking about the things that men and women can contribute to in the greenhouse gases. So water is the primary greenhouse gas. There are skeptics who say water's the dominant gas. The amount of things that we're contributing are probably really minor compared to the effect of water. Other people say no, because the amount of carbon dioxide, which is a greenhouse gas, has really risen precipitously in the last 100 years. Second most important greenhouse gas, there's a few of them. Methane is one of the really important ones. You guys know I went to Washington State University, go Cougs, right? When I was there, they did the seminal research on production of methane gas by bovines. They put little things there to collect their belching and little things elsewhere to collect other emissions from their bodies. And they measured how much methane is produced by cattle, because that's a real contributor to global warming. So I know one of our colleagues here, my colleague, I guess not yours, Chris Blake, he said, I'm a vegetarian because I care for the environment. If you actually believe that man is responsible for global warming, which most people do, the first step you should take is to stop eating meat. Because the methane production from the bovines is much bigger effect on temperature change, the greenhouse effect, than the carbon dioxide that's produced by your automobile and whatnot. But Al Gore doesn't focus on that because it's a lot harder to convince people not to eat meat than it is to convince them that they should drive a car that produces less carbon dioxide. Okay, so I just want to make sure that we have some knowledge about these topics. And I won't go any further in the greenhouse effect because we only got 14 minutes left. So just one question to close that. What would happen if there was no greenhouse effect on Earth? We're actually getting down to the end for the cards, which is good. Okay, we're up to 40 responses. We should have more than that. Okay, about 5 more seconds and we'll move on. All right. We had 0, 5, and 40. Okay, Diamond Taylor, what's your response and your reasoning?
I didn't get a chance to answer.
Okay. Rather than going to another person, I will just go on from there. I saw a commercial once on TV that was envisioning the perfect world. And they said, I see a future where we have no greenhouse effect. And I was like, oh no. Clearly this advertising team does not know what they're talking about. Because if there's no greenhouse effect, then the temperature on Earth is going to plummet and we all become popsicles. That would be bad. So the temperature would drop to an unlivable level if there is no greenhouse effect. We need the greenhouse effect, but we need it within reason. If it becomes too strong, well, then we can't survive. And, if we had time, we could talk about the theories on what happened on Venus so that it has this runaway greenhouse effect. Liquid water is an important thing because liquid water takes carbon dioxide and deposits it in rock. So it takes it out of the atmosphere and puts it in rock. Theory is that it never got cool enough for liquid water on Venus. Hence, it couldn't take carbon dioxide out of the atmosphere. Okay, last thing for this topic, this entire topic of heat mechanisms. Last class period, I brought a doer. Today, I forgot, right? We're not in the classroom where I can grab it easily. But a doer is a device that is used to keep hot things hot or cold things cold. And so you've probably heard that joke about, putting the ice cream and the soup in the thermos together because it keeps hot things hot and cold things cold. Well, it doesn't work and it's funny. But the doer's design, right, if I bring it so you have the naked doer, if you look here, this thing inside, what is inside the thermos, that's the doer. So, we see thermoses. Kelly has, I don't know if that's a water bottle or a thermos, but. Okay. These are designed to stop the 3 different types of heat. So what are the names of the 3 types of heat? Okay, radiation. I wish I could write as fast as you speak. So the design is designed to stop each of those. So let's start with the convection. Convection is an intermediary that carries the heat away. So if you don't have anything flowing, you're not going to have convection. So this is designed so you have a double wall chamber. So you have a glass chamber that has a vacuum in between two walls. If there's a vacuum in between the walls, you can't have any gas moving from one wall to the other. You can't have a liquid going from one wall to the other. So that's going to stop convection. So you'll have no convection through this stuff here that is, let's call it cream colored, because that's a vacuum. Of course, you have to have the top, so the top has a lid on it so you can't have anything escape from that. And that lid is going to have a gap inside to try to, once again, stop convection losses. So convection is blocked by having a vacuum gap. Then conduction, direct contact. Well, whatever is inside is making direct contact with this wall. And so heat could flow from that wall up around here to the outside, and then it could get out, right? So you can't stop the conduction. But the conduction equation for the rate of it was the cross-sectional area divided by the length, multiplied by the change in temperature, and then with that constant K. So they choose glass because glass is a pretty good insulator. It has a reasonably high K value. Or excuse me, reasonably low K value. They make the wall thin, so if you look at that wall, it's thin, so you take the area, length times width, and it's a small area. So they're minimizing the area by making it a thin wall. And the distance it has to travel is large, so they're making A over L the smallest value possible, and thus making the rate for conductive losses as low as possible. And then finally, radiation. You clearly can't see it here, but if I had my doer that I brought last class period, you would see that it's coated with silver. It's coated with silver because silver has an extremely low emissivity. It's very, very poor at absorbing or emitting radiation. And so the silver blocks the radiation. The glass combined with geometry blocks conduction, and the double wall is what blocks convection. And so that doer is designed specifically to stop all of the mechanisms for heat. Finally, I have so much more. In lab yesterday, one of the things we did was measure temperatures. That was really just to help you understand how we choose a good set of reference points for a temperature system. That was pretty simple. Then you studied the rate of heating and cooling, and you should have noted, okay, evaporative effects make an effect on the rate of cooling, and how much contact you have makes an effect on the rate of the heating, right? Because they were two different experiment types. But we also talked about the rate of heating and cooling then in the freezing experiment. And I mentioned that there's a relationship between the temperature change and how much heat you remove. And so here's an intermediary in physics thinking variable, the heat capacity. The heat capacity is simply defined as the ratio of heat to change in temperature. And so if I have a small block, the temperature is going to increase more for the same heat than if I have a big block. So that heat capacity is going to depend on how much material I have, as well as the type of material. So we tend to say, okay, that heat capacity is a good idea, but you know what's even better? A better idea than heat capacity is the specific heat capacity. We usually drop off the word capacity, just say specific heat. And the specific heat is saying, okay, let's just take this heat capacity and divide it by the mass. And so the specific heat is the heat per unit mass required to change the temperature. And so that gives us the equation that we had in lab, Q is equal to MC delta T. Now, you did not use that, but we used it to describe what's going on as heat is drawn out of the water. The heat was drawn out at a roughly constant rate. So if I just take both sides and divide by time, the Q over delta T was roughly constant. Newton's law of cooling says that initially, when you have a bigger temperature difference, it's going to be a slightly bigger rate of cooling. But if you treat those as constant, then you should have had a graph of heat versus temperature is going to have a slope of MC. And so you have graphs that in theory look like this. Now, our graphs, of course, had time running this direction because we were pulling heat out. And our graph should have roughly looked like this. Now, did you guys look at the graphs that I sent you yesterday? No? They didn't look like this. Not at all. You had something that it came down like the first line, but then here it went like this. And I offered a few options on why this could be. Number one is, if it's not pure, the temperature does change while you're freezing. Number two, and probably a bigger issue, is that we had a big temperature probe and it was only like this much into water. And so you're going to have conduction down that probe, and so the actual temperature you're measuring is going to be affected by both the temperature out here and the temperature down here. And I think that played a lot into the curvature. If we had a pinpoint thermocouple instead of having that metal cover, I think it probably would have given us a much flatter look here. Whoops, that's not very flat. But a much flatter look here and a more distinct elbow there. But we saw the rough behavior, but not the idealized behavior. Part of it is the equipment we use. Part of it is, as you probably noticed, none of my containers are anywhere close to sanitary clean. And so there's more impurities in my water than most water. Here are specific heats for different materials. And there's something really important to notice. Specific heat of water, 4.186 kilojoules per kilogram Kelvin. So remember, Q is equal to MC delta T. So since C is large for water, that means if I put in a bunch of heat, the temperature change is not going to be very large because that C is very large. So water is a good temperature buffer, if you will, using a chemistry term. We call it a heat sink in physics terminology. Because if I have water, I can put a lot of heat into it, and the temperature only changes by a small amount. If I solve this for change in temperature, changing temperature is the heat over MC. And since water has a much bigger specific heat than most materials, compare it to iron. We have Pyrex glass. Well, glasses, silicates, those are the common things on Earth. Water is much bigger than that, like more than 4 times bigger. So you take heat and you put it into water, and the temperature is going to go up less than a quarter of what it would have gone up if it had gone into a rock. So if you have a big body of water nearby, so let's say, for instance, that you are in California with a big body of water we like to call the Pacific Ocean. When you have cold air from the Arctic come down, you'll just have a lot of heat flow out of the water into the air to warm up the air, and the temperature of the water only goes down a small amount, which helps to keep the temperature over land much less volatile. So in California on the coast, if you go straight west from here, during the winter, you're not going to have snow at the coast. Here, we're going to have snow. The difference is because California has that big heat sink water there. Here, we are so far away from any body of water, our temperatures fluctuate much more wildly. We're out of time. Have a great day. Do your best to cope with the election outcomes, whatever your feelings are. And I'll see you on Friday.